Let's now go through an example, but before I dig into the example, I recap one of the toy examples that I presented before, so we see this with more clarity. So remember the example I showed before, in which we've got at level 1 are observations and level 2 are participants. And then the variables that we are interested in are the independent variable is the format of presentation, which could be in words and images, and then the dependent variable or outcome variable is accuracy. And basically what we had is 8 observations, and these are 2 participants. 4 observations belong to one participant, and 4 observations to the other participant. And we have here that the observations for words and the observation for images. We've got in red, in white, that's the average intercept and the average slope. So the average intercept is where the white line intersects with words, and the slope it's what is the steepness of that line, and that is negative because it goes down from words to images. And now that's if we finish there, that's the fixed model, in which we have a fixed intercept and a fixed slope. But if we do a random model in which we have a random intercept, then that's the white arrow that goes from the yellow dots to the blue dots, and it shows the variability of the intercept. And then we've got another arrow that shows us the variability of the slope. So how do we know about the variability? Well, the red lines indicate the intercept and the slope for each group. So the red line on top shows that for the first participant there is a reduction in accuracy from words to images, and for the second participant there is a larger reduction in accuracy. So because of that, it makes sense to have calculate the variability of the slope, and also to have calculate the variability of the intercept, not just to have one intercept. Now, as I showed before, we've got models without slope, and in this case this is a model in which we've got a random intercept, but we don't calculate the slope. So in this case, we don't consider at all the variable format, and we assume that all the values they don't belong to two conditions, and basically we've got a random intercept. That means that we are comparing the means of the two groups, how the means of the two groups compare to the total mean. Okay, let's now go to the actual example. So I'm going to use an example with experimental data, and in this case participants will be level 2 and observations level 1. So in this study we measure reaction time, and the task was to identify a word that was presented at different speeds. So the total number of observations is 6,000, and we've got 20 participants. The predictor or independent variables are presentation time, which was fast presentation, medium presentation time and slow presentation time. So the words were presented or either very fast or very slow. And this was a within subjects variable. So basically, all the participants went through the 3 conditions. But then we've got a time of the day variable, which is within subjects. So some of the participants, 10 participants, conducted the study in the morning, and 10 participants conducted the study in the afternoon. The outcome variable was reaction time, so how much time the participants took to identify the presented word. Now, this is a typical study in psychology, in cognitive psychology, in perception, attention. Why are we going to use multi-level modeling here when we typically don't use multi-level modeling? Okay, let's see why. In this case, we've got for each participant 100 fast observations, 100 medium, and 100 slow. So each participant contributes 300 observations. And we've got 20 participants, so 20 times 300 is 6,000. So these are all the observations we have. And as I said, 10 participants do this in the morning and 10 in the afternoon. Now, the levels that we can use for this study is the individual is level 2 and observation is level 1. So in this case, we've got for individual number 1, we've got 300 observations. So it goes 1, 2 to 300. For individual 2, we've got observation 201, 202, up to 600. For individual number 3, we've got again 300 observations, 601, 602, up to 900, and so on and so forth. So the last participant 20, has observations 5,701 to 6,000. So again, observation is level 1 here, and participants or individuals are level 2. So observations are embedded within the individuals, and using the 6,000 observations to do the linear model without considering that they belong to different individuals is incorrect, because the observations within each individual are correlated. They are more similar to each other than that of other individuals. Okay, so we've got here again the level of observation, which is level 1, and level individual, which is level 2. And the variables in level 1 are reaction time, which is the dependent variable, and time of the day and presentation are the independent variables at that level as well. At the individual level, we've got a variable which is age, which is measured at that level. It's not measured at the level of observation. The observations don't have age, the individuals do. We can, if we wanted to try to use age as a predictor of reaction time, but we are not interested on that in this study. Okay, some descriptive statistics. That's the whole data. This 6,000 observations, and all they are in a plot with a violin plot and some jittering of the data. This is the distribution of the reaction time, and this is reaction time in each participant, so a violin plot in each participant. So that tells you that how all the reaction times are embedded within the participants. And this is statistics that don't take into account the participants, so these take into account the conditions. So in the x-axis we've got fast, medium and slow, and you can see that the slower the presentation time, the slower the reaction time. which is sorry, not the slower the reaction time, the smaller the number of the reaction time. That means it's faster. So a small number in reaction time means that people are responding faster. And also indicates that people respond faster in the morning than in the afternoon. But this is visual. We need to corroborate with the multi-level modeling analysis. Now, the traditional approach in this case would lose a lot of data, because as I said, participants have 100 reaction times in each condition, right? So this will be averaged for each participant. So in the traditional approach, these 100 observations that each participant contributes, they become only one. We obtain the mean of these reaction times, and that's all we have. So if we use the traditional analysis, then we will have 10 observations for each condition. So that is 60 observations only. So of the 6,000 observations we started with, by averaging, we only get 60. That's a loss of data that is not desirable. So that's why if we use multi-level modeling, putting participants as level 2, then that allows us to use all the data. Okay, so I created 4 models. Model 0 is a random intercept without an independent variable. Model 1 is random intercept and time of the day as independent variable. Model 2, a random intercept and time of the day and speed as independent variables. And then model 3, we have a random effect of time and speed. So I should have said that in models 1 and 2, the effect of the variables is fixed, is not random. And basically, this is how the results are presented in multi-level modeling. So we've got models, the 4 models in the columns, and then on the left-hand side we've got some information about titles or labels of parameters that we are estimating. So in terms of fixed effects, we've got the intercept. So the intercept for model 0 is 776, and this is the milliseconds of the reaction time. And for model 1 is 775.6, model 2 is the same, and model 3 the same. So not much variability in terms of the intercept of the different models. Now, if you look at time model 0, it doesn't incorporate time of the day as independent variable or speed of presentation as independent variable, so there are no fixed effects there. But it has a random component, which is the intercept, and this value 7,253 is the variance. So the point estimate of the intercept is 776. So this is the mean intercept for all the participants. But the model assumes a variability. So it means that for the participants, we cannot assume that they all have the same intercept. They vary in their intercept, and that is the 7,253. It's the variability or the variance of the intercept. And the residuals, that is the when we've got in a linear model, we remember that we've got 2 versions. In one we have the error or epsilon, and that would be here the residuals would be that error. Or it would be when in the second version of the way I presented linear models, we have in order to predict each of the observations, we have a normal distribution with a mean given by the model and the standard deviation sigma, which is estimated. These residuals is equivalent to that standard deviation. The difference is that typically in multi-level modeling, there is a tradition of reporting the variance instead of the standard deviation. So the variance is the square of the standard deviation. And then we've got AIC. So we can use BIC, AIC, and there are other measures as well. But well, we've got 63,208. What does it mean? Doesn't mean anything. We don't care about that absolute value because AIC and BIC are measures that are useful to compare, but in itself they don't mean anything. So let's go to model 1. In model 1 we got the fixed effect, the intercept, and we've got another fixed effect, which is time of the day. And in terms of time of the day, what parameter that is presented there is how the morning condition compares to the mean of the two conditions. So that means that the reaction time is lower in the morning condition than in the mean of the two conditions. So that we expect that in the morning the reaction time will be 51 milliseconds faster than the mean of the two conditions. And that is the same in model 1, model 2, and model 3. Now, in terms of the intercept, now we have less variability. So when we add a variable, that changes the variability of the intercept. So instead of 7,253 in model 0, we've got 4,667. And the residual is the same, 2,155. Now, what happened to the AIC? 63,192. So that is 16 points of BIC lower in model 1. That means that model 1 is better than model 0, because the lower the AIC, the better the model. So if that's the case, it means that adding that fixed effect of time of the day fixed effect was useful. So that means that time of the day has an effect over the reaction time. Now, in model 2, we continue with time of the day. That doesn't change, but we add the second variable. We add the slope of speed of presentation. And speed of presentation has 3 possibilities: slow, medium, and fast. So we need to create dummy variables like we did when we did a Bayesian ANOVA. And so basically what is saying that in speed of presentation, the condition medium over the mean of the 3 conditions, you expect 4 milliseconds slower. Whereas in the slow condition over the mean of the 3 conditions, you expect 45.1 milliseconds faster. And that's the same in model 2 and in model 3. In terms of the intercept for the whole linear model, it goes from 4,667 to 4,671. So a slight change, a minor change in the variability. Now, what about the residuals? The residuals reduce dramatically from 2,155 to 902. So that means that overall, when we do the prediction of each of the observations, the predictions are much better because the residuals are lower. And the AIC goes from 63,192 to 57,980. That's a massive decrease in AIC. That means that speed of presentation, it's a very important variable, more important than time of the day. Look at the reduction in the AIC, much more when we add speed of presentation. Okay, so model 2 has the two independent variables as fixed effects, not as random effects. So in model 3, for speed of presentation, we add a random effect, and so that means that what we are saying that for all the participants, we should expect a different slope of speed of presentation. So some participants will there are differences in between these conditions will be larger than in other participants. So that's what the Model 3 is saying or is claiming. So in terms of the fixed effects, so this will be the average speed of presentation slope is the same as before, 4 and negative 45.1. But now we have the variability, and the variability of the medium over mean parameter is 941, and the slope over mean is 476. How about the residuals? The residuals go down, and go down dramatically again. So that means that it is hinting that towards that adding the random component for the speed of presentation was important as well. But let's corroborate with the AIC. The AIC says 53,922. Again, so that means that Model 3 is better than Model 2.